Hello and welcome everyone to the second lecture on semiconductor electronics. In the previous lecture, we have talked about the structural aspect of the solid. In today's class, we shall try to classify the solid on the basis of their property of conductivity into three categories such as conductor, semiconductor and insulator. Okay, so as the name suggests, conductor is something which conducts electricity in a very good sense, and insulator is something that prohibits the conduction of electricity through the solid, and semiconductor is a type of solid where the conductivity lies somewhere in between that of the conductor and the insulator. Okay, so let us try to go in detail about the three types of solids on the basis of their which can be classified on the basis of their conductivity property. So let's first discuss about the conductors. Now, in general, the conductors are the metallic objects, or so as to say the metals. Now, metals have very high electrical conductivity. For example, you have iron, copper, aluminium, tin, gold, the titanium, zinc, etc. So these are all very good conductors of electricity as well as heat, and we all know about it. Now, metals are something that follows the Ohm's law. Now, Ohm's law, in the sense, we are we are familiar with the type of Ohm's law where we have found a direct relation between the voltage applied across an object and the current. So there is a linear relationship between the voltage and the current. However, the Ohm's law can also be stated as the current density J, which is a vector quantity flowing through a metal, is proportional to the applied electric field E. So for example, you have a metal somewhere. In that case, if you apply an electric field with the help of a battery, in the case you will find that the current flowing through it is directly proportional to the electric field which has been applied across this. Although this part is not included in your syllabus, but as an extra knowledge, you can gather these things. So if you just remove this proportionality sign, we know that we have to put a constant of proportionality, which we have put here as sigma. Now this sigma is nothing but the electrical conductivity. So how actually we define the electrical conductivity? Electrical conductivity can be defined as the ratio of the current density per unit electric field. All right. So if per unit electric field the current density is high in some material, in that case that's a good conductor as compared to the others. Now the resistance of some metals vanishes at around absolute zero temperature, which displays the phenomenon of superconductivity. Now resistance is directly dependent on the temperature, for example, because as soon as the temperature increases in the metal, resistivity increases. Okay. This situation is quite like in electrons, the electrons which are there in the metals are free electrons. That means they are freely available or freely movable. Their mobility is very high. So as soon as you apply an electric field across the metal, they try to go at the same time. And that as a result of that, every electron tends to move and ultimately they create a blockade or a jam. For example, on highways, you will find that whenever the highway is suppose empty, and recently suppose there was jam initially and recently the cars were released. At the time what happens, every car wants to go or wants to pass a particular region. In that case, that unnecessarily creates a jam. So that is similar thing happens even in the case of a metal. So when all the electrons tends to go at the same time, they create a jam kind of a situation, and that results in increasing the resistance. Now the ratio of the thermal to the electrical conductivity of a metal is proportional to the absolute temperature. And thus if you take the ratio, this is the thermal conductivity to sigma, that is electrical conductivity. If you take this ratio, that is directly proportional to the temperature. And if you remove this proportionality sign, once again you have to put a constant of proportionality, say L, which is known as the Lorentz number. And in that case you get the K upon sigma, that is thermal to electrical conductivity, is equal to Lorentz number times the temperature. And this whole law, this is a law which is known as Weidmann and Franz's law. Okay, so this is all about conductors. Normally conductors are good conductors of electricity. They are very smooth conductors of electricity. All right. Now coming back to insulators, we know that insulators are not as good conductor as conductors, or rather they are not at all they do not at all conduct the electricity. For example, you can see over here, here you can see some copper wires which are coated with some kind of a material, and that material is actually an insulating material. The reason this is coated so that you do not get an electrical shock or there is no electrical hazard. Similarly, whenever you see the electrical poles, you will see that there are some kinds of cup-like structures. These are also insulators. Okay. Now, an insulator is a material that does not conduct electricity at all. For example, plastic, paper, rubber, glass, air, etc. In fact, vacuum is also an insulator because it doesn't carry electricity. However, we cannot say in that sense because vacuum is not actually a material. So that is the reason why vacuum also doesn't conduct electricity, but even then we cannot call it to be an insulator because there is a controversy actually, because many times people would like to call it to be an insulator, but this is at the end it's not at all a material. So from that material sense we cannot call vacuum to be an insulator. All right. Most electrical conductors are covered with insulators. Insulators keep electrical conductors from making unintended contact with each other. For example, you have got two wires, as you can see over here. This is a copper wire which is insulated, and this is another copper wire which is also insulated, such that they do not make any contact with each other. That is why this insulated coating is required. Okay, so although insulators do not conduct electricity, but they have their own advantages of that. Okay, we require insulators as much as we require the conductors. Now, there is an in-between class which carries the electricity but not as good as the conductor or as bad as the insulator. So their conductivity lies somewhere between the conductor and that of the insulator, and they are known as semiconductors. So as a definition, certain substances are neither very good conductor of electricity such as copper or aluminum, nor a bad conductor of electricity such as glass. So these substances have their conductivity lying in between the conductor and insulator, and they are known as the semiconductors. So that is the reason why semi word is there. For example, we know semi-classical, something which is not purely classical and not completely modern, somewhere in between. So that is a semi-classical. So here also, which is something not very good conductor or not insulator also, somewhere the conductivity lies in between, that is known as semiconductors. But semiconductors have got wide range of applicability in electronic circuit. In fact, you can say in today's electronic industry, whatever you see, starting from the remote that you are using, inside that remote you have got certain designs of PCB, the printed circuit boards, the elements which are there. You can see the LEDs today, the light emitting diodes, LED bulbs are there, LED TV is there, everything, transistors, I mean, diodes, everything that you can see today, modern switches, they're all made up of semiconductor materials. Okay. Now, I would like to draw your attention to a particular thing at this point. Just look at the group 4 element of periodic table. Now, in the group 4 element, you can see there are carbon, silicon, germanium, tin, and lead. Now, if you see the conductivity behavior of these elements, you will see a peculiar behavior. And the peculiar behavior is the carbon is behaving like an insulator. Carbon is not at all a conductor, or neither is a semiconductor. However, in between carbon and tin, which is a conductor, you have got silicon and germanium. Now, silicon is semiconductor, germanium is also a semiconductor. On the other hand, you have got tin and lead, both are to be conductor, although not very good conductors, but yet then conductor. All right. So how come that in a single periodic element, I mean single group elements like group 4 elements, you have got all three classes of conductivity lying together, such as carbon is an insulator, silicon, germaniums are semiconductors, whereas the tin and lead are conductors. How come this is possible? So in the side figure you have been given, I have shown the electronic configuration of all these elements. Now, in order to answer this question, why these three kinds of conductivity property we achieve in a single group of element, we have to understand something called band theory. Okay, band theory means whenever the solids, for example, carbon atoms, you can say, or silicon atoms, you can say, whenever they come close together to form the solid, in that case, they form certain energy levels. Now these are no longer certain energy levels or discrete energy levels, they form a energy continuous energy band, and that band formation is actually the reason why we have got three different kinds of conductivity into the single periodic group element. All right, so let us try to see that how exactly is this possible. Now before we go into the concept of band formation, let us try to understand the energy levels. Now the concept of energy levels comes from the Bohr's atomic model. So this is something which either you have encountered already or you are going to encounter very shortly. Now Bohr's atomic model means, you know about, I hope you are aware of the atomic models. We have Rutherford atomic model, we have J.J. Thomson's atomic model. Similarly, the most modern, you can say, not most modern, although there are vector atom models, there are wave mechanical models, but otherwise almost a well accepted model is the Bohr's atomic model, which says that inside an atom you have got a nucleus. Within the nucleus you have got protons and neutrons, and the electrons, they revolve around this nucleus in definite circular orbits. That is what is a Bohr's atomic model says. Now the electrons which are there into these orbits, the orbits define their energy. For example, the electron which are there close to the nucleus, for example this orbit is closer to the nucleus, this orbit is little bit farther away from the nucleus. So the electrons which are in the farther position, they have got a different energy structure, and the electrons which are there in the near orbit, they have got a different energy levels. All right, so that is why each electron will give rise to a separate energy level. All right, so they will be discrete energy levels. And how exactly can electron gain energy? For example, you can see over here, an electron was initially revolving here, then suddenly from somewhere it gets an energy, and once it gets an energy it goes to the higher orbit. So definitely the electron which are in the higher orbit, they have got higher energy. Electrons which are orbiting in the lower orbit, lower in the sense close to the nucleus, they have got lower energy. So an electron absorbs energy from external source and then goes to the upper orbit. In the upper orbit they release the energy and again comes to the lower orbit. All right, so an electron can release energy to come down in orbit, and an electron can gain energy to go up in the orbit. Okay, so some electron may gain energy. If the electron gains energy, they will make a transit to higher energy levels. If an electron at higher energy level loses some portion of the energy, that will come down. All right, so that's how electron makes a transition to the higher orbits or higher energy levels. Got it? Now these are discrete energy levels. For example, an electron have either energy of the order of say 13.6 electron volt, or it can have an energy of 5.6 electron volt. There is nothing in between. You cannot have an electron, suppose, with an energy of 4.8 or 4.2 electron volt. It is discrete. Either you have got 13.6 or you have got 4 or you have got 5.2, say for example. There is nothing in between. So that is why it is called discrete energy level. For example, you can see there are no orbits in between. So that means there are no electronic levels or no electronic energy levels in between these two. An electron can either occupy the space in this orbit, or it can occupy a space in this orbit. It cannot be somewhere in the middle. So that is why that gives rise to the concept of discrete energy levels. However, this is true only for an isolated atom. For example, you talk about a hydrogen. If you keep an hydrogen atom isolated, it is not in near neighborhood of other hydrogen atoms, then this theory is correct. But whenever the atoms come close together to form a solid, because whenever you want to form solid, the atoms must come close together, because otherwise how would they form the solid? In that case, what happens? The outer orbits of electrons from neighboring atoms would come very close or could even overlap. For example, if this is a total atom, similarly there are 5 other atoms in near neighborhood of this, then what will happen? The outer orbits, they will overlap with each other. There is a possibility that they will overlap with each other. And in that case, what will happen? The energy levels will no longer be discrete, they will be continuous in the space. Alright. So hence the nature of electron motion in a solid is very different from that of an isolated atom. In an isolated atom, as you can see, the electron is very nicely revolving around the nucleus. But this is an isolated atom. whenever there are five such atoms in the near neighborhood, the dynamics of this electron will change. It will not revolve nicely, as you can see in this picture. That will not revolve so nicely. It will have a complicated motion. Its motion will become very complicated. All right. So that is something which we give, which we get in an energy band. So let's now go into the concept of energy band. Now energy bands, they are formed whenever two or more atoms they come close to each other. For example, now here you consider this is one atom, their black dot is a nucleus, and this is another atom with this is the electronic levels. The white portion that shows the total atomic dimension, and the black dot, it shows the nuclear dimension. That means that is the nucleus. In that case, what will happen? The nucleus is positively charged, as we all know, because nucleus contains the protons. Neutrons are also there, but neutrons are chargeless particles. So in that case, what will happen? These particular nucleus will be attracted to the electronic cloud of this particular atom. And similarly, the nucleus of this atom will be attracted to the electronic cloud of this particular atom. Okay, that means the electrons of this atom will attract the nucleus of this atom. The electrons of this atom will attract the nucleus of this atom. All right, so this is an attractive bond. You have got nucleus to nucleus repulsion. Why? Because this is positive charge, this is positive charge, they will repel each other. And similarly, the electronic cloud and electronic cloud, they will also repel each other. So you have got uh, one type of attraction, that is electronic cloud to the nucleus, and two types of repulsion, that is nuclear repulsion and electronic clouds repulsion. So as a result of what? As a result of this, whenever they come close together, for example, they are now at least situated certain distance apart. Whenever they come close together, these electronic cloud, which you can see over here, they may also get overlap. In that case, they will have different energy levels. Now we know that energy levels of atoms are like discrete, for example, like this. But whenever they come close together, the energy levels start perturbating. For example, these energy level got splitted up into two, these energy level got splitted up into two, and ultimately you see there is no distinction between whether this is an energy level or an energy band. Okay. So I will explain this particular picture in greater detail. In this picture, we have the energy on this axis and the interatomic spacing on this axis. Interatomic spacing means the distance between two atoms. So distance between two atoms are high over here whenever this D position is there. Here the distance is very high. As you come this side, the distance between two atoms is decreasing, right? So let's see what is written over here. Inside a crystal, each atom, each electron has a unique position, and no two electrons see exactly the same pattern of the surrounding charges. Therefore, each electron will have a different energy level. These different energy levels with continuous energy variation form what are called the energy bands. Now the energy band, which includes the energy levels of the valence electrons, is called the valence band. The energy band above the valence band is called the conduction band. I will explain in detail how exactly this valence band and the conduction band are formed. This is CB means conduction band, VB means valence band. With no external energy, all the electrons will reside in the valence band, and the conduction band is practically empty. Okay. So this gives rise to an idea of the formation of energy band, but although not very clear picture, in the next slide I will explain bit by bit of this particular phenomena. Okay. So here all the paragraphs are very important. So please go through these paragraphs if you do not understand. In case you can pause for a while at this particular slide, and you can look at these paragraphs very carefully, because these refer to this diagram and go for these paragraphs which are there. Now this diagram, as already I said, on the x-axis it shows the interatomic spaces between two or n atoms, and on the y-axis we can see the energy of different levels. Now we know that, suppose here I have shown the energy levels of silicon atom. Silicon, the electronic configuration is already shown in the previous slide. For example, you can go back here. Here you can see the electronic configuration of silicon: 1s2, 2s2, 2p6, 3s2, 3p2. I hope you understand this meaning. For example, this is the principal quantum number: 1, 2, 3, and 3. Means level 1, level 2, level 3. So in that case, what you have in the level 1, you have got only s orbital, which can accommodate 2 electrons, and it has already 2 electrons. That is why 1s2. In the second level of silicon is splitted up into s orbital and p orbital. The s orbital can accommodate 2 electrons and 2 electrons are there. P orbital can accommodate 6 electrons and 6 electrons are there. Then in the third level is now splitted up into 3 level actually, s, p and d. But since silicon has got 14 electrons and already 6 plus 2 plus 2, that is 10 of them are accommodated already in the first two levels, in the third level the rest of the 4 electrons can be accommodated, out of which in the 3s level already 2 electron can be there, so it has occupied. And in the 3p level, the p level can accommodate 6 electron, but silicon has only 2 electrons to be accommodated then, so 2 electrons are occupied, rest 4 levels are empty. All right, so this is what is an electronic configuration of silicon. In chemistry classes, hopefully we'll understand this better. Now let's come back to this particular picture. So let us consider a single silicon crystal with n silicon atoms. N is very large. In a crystal, you can essentially get many different types of many different atoms. For example, of silicon crystal, if you talk about, in that case it will be of, say, if you take 1 mole of a silicon, in that case it will be 6.023 into 10 to the power 23 numbers of atoms. So you can guess the amount of silicon atom in a crystal. So this n is naturally very large number. Now in order to form the crystal, the silicon atoms must come close together and sit in their respective lattice sites. If the interatomic distance is large, there is no interatomic interaction. For example, one silicon atom is sitting over here, another silicon atom is sitting over here. The distance is very large and hence there is no interaction at all. But once they come close together, there will be interaction. So refer to this diagram. When the silicon atoms are at level D, that means the interatomic spacing is quite high, then there is no interaction. So you have got splitted energy levels. I mean, you have got individual energy levels. But when the silicon atom interatomic spacing is C, for example here, interatomic spacing has now decreased. In that case, the interaction between the outermost shell 3s2 and 3p2 of neighboring atoms become appreciable. You can see these two levels have started splitting, and this splitting occurs because of the interatomic interaction. These two energy levels, or the electrons which are residing in these energy levels, they interact with each other electronically or electrostatically, and that gives rise to the different energy status of these levels. Whereas the lower orbit electrons, they do not interact. See, you have got discrete energy levels. As a result, the energy levels start splitting. You can see over here, no change occurs to the energy levels of the inner shells, as already I have explained. Now, when the interatomic spacing is between B and C, now even reduce more. It was initially at C, now reduce more, come to B. So in between B and C, we get a large number of closely packed levels. For example, twice n level corresponding to 3s and 6n corresponding to 3p. Why this n is there and why is 2 is there? Because s orbital can take 2 electrons. If there are n atoms, n different atoms accommodating 2 electrons in their s orbital, that gives rise to twice n levels, and p orbital can accommodate 6 electron, so there is a possibility of 6n electrons in the 3p. So these twice n plus 6n, that is 8n actually. This reduces the energy gap which existed in the silicon. For example, you can see in the 3s and 3p there is a gap of energy, but as you come to B and C, in between B and C, this gap is reduced. Now they are overlapping. See, an electron can be here, 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 or here at any point. So this collection of closely packed energy level is called energy band. So initially you had got discrete energy levels, now you have got energy band. So right from here, this zone is called energy band. Band means, already you know, when you bring something together, that's called a band of, say, sticks. In that case, many sticks come close together, that's a band. Now if you further reduce these electronic levels, if you further reduce this interatomic spacing, in that case these two bands overlap with each other. Here at least you have some gap, but here you see you do not have any gap. But if you further reduce the interatomic spacing, then they split even further. So 4n energy levels goes up, 4n energy levels comes down. So total 4n plus 4n is 8n. Okay. Why 8n energy levels? Because p orbital can accommodate 6 electrons. That means it has got 6 energy levels. S orbital can accommodate 2 electrons. That means it has got 2 energy levels. So 6 plus 2 is 8. So one silicon atom have 8 energy levels in its outermost orbital. So how much outermost orbital energy level will be for n atoms? It will be 8n. So that is the reason why out of that 8n, 4n goes up, 4n comes down. Those 4n which are empty, these are known as conduction band. Those 4n which are now filled with electron, because how many electrons are there? 4. 2 plus 2, 4. The 4 electrons are contributed by a single silicon atom. N silicon atoms will contribute 4n. So that is why these 4n levels are filled with electrons. These 4n levels are empty. So the filled levels are known as valence band. Okay. So that is what has been layered. The lower band, which is completely filled means completely filled with electrons, is called the valence band. And the upper unfilled band is called the conduction band. This unfilled band is called the conduction band. And the valence band and the conduction band are actually separated by a certain gap, which is called the forbidden gap or the forbidden band. In the forbidden gap means no electron can occupy a region in the forbidden gap. It can either be in the valence band or it can be in the conduction band. Alright. So this is how the band forms in silicon atoms. Now on the basis of this band formation, you can further classify metal, semiconductor and insulator. I will not go into the details of this. Just look in the diagram which has been given. In the conductor, you have got the valence band and the conduction band to be closely spaced. There is no gap in between the valence and the conduction band. Okay. In the semiconductor, this gap is minimized. For example, small gap is there. And in case of an insulator, you have got this band to be very high. The forbidden gap or the gap which is not acquired by an electron, that gap is very large. So an electron requires very high energy, because whenever you give energy to the electron, it goes from the valence band to the conduction band. Why? Because electrons are all residing in the valence band. Conduction band is empty. So that is why whenever an electron in the valence band gets some energy to cross this barrier, it goes up to the conduction band, and once it reaches conduction band, it becomes free. It is no longer bounded. And whenever it is free, it can roam anywhere. So that is the reason why whenever electron reaches conduction band, it gives rise to conductivity. So in insulator, there is no way that an electron can reach from the valence band to the conduction band. So conduction band remains always empty with no electrons being there, and hence there is no conduction possible in the case of an insulator. Alright, so that is why insulator is a non-conductor or bad conductor of electricity. Whereas in the case of a metal, the conductivity is very high, because an electron can often jump from valence band to the conduction band as there is no gap. So that is why conductivity is very high. And in the case of semiconductor, an electron can jump only if you provide an external energy to these electrons such that the electrons can jump from the valence band to the conduction band. And once it goes to the conduction band, it gives rise to some conductivity. So that is why semiconductors are not very good conductors, but if given energy, electrons will be liberated from valence band, they will go to the conduction band and will increase the conductivity. Alright. Now, how exactly an electron goes up and what happens to the valence band? So, whenever an electron goes up from valence band to the conduction band, it creates a empty space in its location in the valence band. And that empty space in the valence band of a semiconductor has a meaning, and it is known as a hole. Hole means an empty space. Its hole doesn't mean anything. Hole means an absence of an electron. It is just a name. Okay, hole means the absence of an electron. So a hole is considered to be a seat of positive charge. Why positive charge? Because it is devoid of electron. An electron has moved out of it. So that is why it is positive. Alright. So it is a seat of a positive charge having charge equal to that of an electron. For example, what is the charge of an electron? Minus 1.6 times 10 to the power minus 19 coulomb. Then what is the charge of a hole? It is plus 1.6 into 10 to the power minus 19 coulomb. So hole is an active particle in the valence band as the electron in the conduction band. For example, electron moves in the conduction band, hole moves in the valence band. The motion of electron in the conduction band and hole in the valence band constitutes the conduction current in a semiconductor. That is an interesting part. The semiconductor current is given by two entities. One is an electron, another is a hole. Because you have conduction both in the conduction band and in the valence band. In the valence band, hole conducts the electricity. In the conduction band, electron conducts the electricity. So that is why conductivity of a semiconductor is given by both hole conductivity and electron conductivity. Whereas in case of a metal, it is only the electrons which conduct electricity. But in the case of a semiconductor, two quantities carry electricity. One is a hole, another is an electron. Alright, so here you can see a diagram where I have applied some potential difference. This is a hole, an electron moves into the hole, and it is as if the hole moves leftward. You see, this is a positive charge representing a hole, started right, then coming left. Got it? So that is what is a concept of hole creation in the case of a semiconductor and hole conductivity. Now, how you can total, what is the big picture of the semiconductor? The big picture of semiconductor is semiconductors can be now classified into two categories mainly. One is an intrinsic semiconductor, another is an extrinsic semiconductor. Now, intrinsic means the semiconductor in which you have got number of holes and number of electrons to be same. However, in extrinsic semiconductor, the number of holes and the number of electrons are different. Alright. Now, if the number of hole is less than that of the electron, then it is called n-type semiconductor. If the number of hole is more than that of the electron, it is called p-type semiconductor. Okay. So we will discuss it in the next class, how exactly the p-type and n-type semiconductors are formed, and how definitely for forming p-type and n-type you need to go for doping, something called doping. Doping means adding impurities to the intrinsic semiconductor. Now remember that intrinsic semiconductor means germanium and silicon. These two are the intrinsic semiconductor. Means if you just take a single crystal of silicon or single crystal of germanium, you will have number of holes and number of electrons to be same. And that is why they are known as intrinsic semiconductors. But if you dope, if you add some impurities into silicon or germanium, they will either behave as n-type extrinsic semiconductor, or they will behave as p-type extrinsic semiconductor, depending on what kind of impurity you have doped over there. All right, that we will discuss in the next class. So this is all about today's class. Thank you so much.